Hello students, in this video we cover the topic of copula fitting. By now we are decently familiar with copulas, what they are, and we have seen several specific examples of copulas, the Gaussian copula, the comonotonic copula, the Gumbel copula, the Clayton copula, etc. The topic that remains is if you're trying to build a multivariate model for your data, you need to fit a copula to your data. How do you do that? Those copulas we've seen, they have parameters. So by fitting, I simply mean estimating the parameters of those copulas. This is the topic we cover now. I should say here we cover it conceptually. So in a separate video, we're going to actually implement how to do the fitting in R. But for now, we're really at the conceptual level or theoretical. So as I said, the big question now is, how do we estimate the parameters of our copula? So again, the situation is this. We have multivariate data. So let's say that you want to capture the dependence between some random variables x1, x2, blah, 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 up to xk. And you want to use a copula to capture this dependence because we saw that via Sklar's theorem, or because of Sklar's theorem, it makes a lot of sense to capture the dependence using a copula. This copula has some parameters that now you want to estimate. This is completely analogous to what you do in the univariate case. You have some data, you make the assumption that a certain univariate distribution is a good representation of this data, and you want to estimate the parameters of this distribution. Now we want to do the same thing with the parameters of our copula. And so what we saw with Sklar's theorem is that in theory we can select the margins and the dependency structure, the copula, completely separately. So if I have my variable x1, x2, blah, blah, I could first investigate what x1 looks like, and I pick whatever random variable to describe it, exponential, log normal, etc. I do the same with x2, I do the same, blah, blah, blah. I don't worry about the dependence, and then eventually I look at the dependence, and then I want to pick a copula to fit this dependence. Maybe there's a upper tail dependence, or maybe I make the assumption that a Gumbel copula would fit well, and so I do that. And I can, those two choices are separate. Okay, this is what we say here. But now in terms of fitting, in principle, you can do the fitting together, meaning that once you've chosen the margins and you've chosen the copula, in one big step, you do the fitting and you estimate all those parameters, both the parameters of your margins and the parameters of the copula, or you can do the fitting separately. And frankly, this makes more sense to me, and I think that's more common, that you estimate the parameters of the margins. That's one step, and then you estimate the parameters of the copula. That's a second step. Okay, and you do answer the fitting separately. Okay, so let's move on. I suppose, as in the univariate case, there are a few different ways you can do the fitting. The first one presented here is quite simple, and it's going to rely on our previous friends, tau and rho. Okay, Kendall's tau and Spearman's rho. The approach is this. You can express the copula parameters as a function of those things, tau and rho. And you can do that theoretically. Let's say, take a specific example, take the Gumbel copula. Well, it's possible to derive what tau is as a function of the parameter of the Gumbel copula, and it's possible to derive what rho is as a function of the parameter of the copula. And so you can do a sort of method of moments then here to estimate the parameters, because and I think let's actually look at the specific example here. We previously saw that for the bivariate Gumbel, let's say that you have the Gumbel copula that characterizes the dependence between x1 and x2. It is the case that the tau, Kendall's tau between x1 and x2, is this simple function of the parameter. Okay, here theta is the single parameter of the bivariate Gumbel copula. Now, invert the relationship. Express theta as a function of tau, and that gives you a recipe to estimate theta, because you know how to estimate tau. We saw previously that there's a pretty simple estimator of the quantity tau that represents the dependence between two random variables. So here you see it's a sort of method of moments because we start from the theoretical relationship of tau as a function of the parameter. We invert it to get the parameter as a function of tau. And now we can compute an estimator of theta because we know how to estimate tau. Like in the method of moments for univariate fitting, we know very well how to obtain estimates of the moments, okay, estimate of, we know how to estimate the expectation by the first empirical moment that we've denoted M1 and so on. Or you know how to estimate expectation of X2 by M2, the second empirical moment. So here you see it's an analogous method to estimate our parameters, our copula parameters. And I think that's all I'm going to say about this method. You might have guessed that what we want to do actually, or the main thing, is the maximum likelihood method. Well, first things first. Let's just remember that what a copula is, okay, the notation here, big C. The copula is a multivariate CDF, but specifically with univariate margins, okay? This is just by definition, this thing is a multivariate CDF where all the margins are uniform 0, 1. The copula density then, we can then obtain it like that. You just take the derivative k times of your initial copula of the big C, because remember, this should be something you've seen in your stats courses. Let's just say that you have a bivariate CDF, just big F of xy. Okay, this represents the joint distribution of two random variables, say big X, big Y. That's the joint CDF. You can obtain the joint density, okay, so denoted little f, by simply taking the derivative twice. Well, you derive with respect to both argument x and y. Okay, when you derive this twice with respect to both arguments, you get to the joint density, little f of x, y. So here, this formula does exactly the same thing, just k times, because the copula is a function of k arguments. So again, sorry if I'm repeating myself, but this is a joint CDF. If you derive it k times with respect to every argument, you will get to the joint density. And the joint density of a copula, in this case, we denoted little c. Okay, so careful here. Over there, we have big C, and here we have little c. Okay, little c being the density. So little c, by definition, must be a multivariate density function, a multivariate PDF, but of course, for which every margin is a uniform 0, 1, because you started from the copula, which is the CDF, with uniform margins. And we're going to use this little c in a moment. You'll see why it matters. Now the thing is, if we had a sample of observations, okay, here careful, it's a bold U, meaning it's a vector. So U1, U2, etc. So this is a sample. If we had a sample where the margins are uniform, okay, so then you would say, okay, all those U's, they follow exactly the distribution big C. They are vectors within which every variable is a uniform 0, 1. So you can say they follow the copula, because remember, the copula is a CDF where the margins are uniform. Now, if this was the case, if you had such a sample, estimating the parameter or parameters in full generality, there could be one parameter, but there could be several. Estimating this parameter, you could do this using maximum likelihood without specific difficulties, okay, as usual. But of course, in reality, you're not going to have data that has uniform margins. So in the next slide, we're going to see the solution to this. Now, just here, the terminology can get a bit cumbersome, so let's be careful we understand. those U1, U2, blah, 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 in general, call them UJ, they are K-variate. So this is why it's in bold here. UJ is shorthand notation for UJ1, UJ2, UJ, blah, blah, up to UJK. Now, what is K? It's simply the dimension. So here, maybe it helps to give a specific, to think of an example. Let's say that you want to analyze the dependence between K stocks. Well, K would be the number of stocks you have, but then let's say that you check the value of the stock every day, okay? So then N would be then the number of days you've collected. So again, imagine that this J here then represents the day, and you have N days in total. So let's say that the first stock would be whatever, the value of Google, and then the second stock would be, well, different stock, the value of Apple, and so on. So here, this would then represent, okay, on the Jth day, this was the value of Google, this was the value of Apple, etc. But then the dependence you're trying to analyze is the dependence between those K stocks. Okay, it's not the dependence between the days, because the days, at least for now, they're considered independent, meaning, yeah, the day 2 is independent of day 1, and etc. The dependence you're looking at is the dependence between the first stock, the second stock, the third stock. I hope that makes it a little bit clearer, but do be careful about the notation here. Okay, now that's the setting. And again, what I said is you would like to have data that is uniformly distributed, because those uniforms exactly have the copula C then. In reality, what you have is some vector here, again denoted bold because it is in several dimensions. So bold X would be X1, X2, blah blah blah, up to xk. And those individual margins, the point is that they are not uniform. So this X1 in general is not a uniform 0,1. This X2 is not a uniform 0,1. Remember, X1, if it's the price of Google on any given day, well, it doesn't have a uniform distribution, of course. Again, in terms of notation, careful. We're going to call bold X1, bold X2 a sample from the vector X. So again, Xj would be, on the jth day, in my example, the price of Google, on the jth day, the price of Apple, etc., and the price of Netflix, and so on. I would like those X's to have uniform margins. That's not the case, but here, I suppose, we use what we could call a trick. Assume that you have estimates of the margins, okay, the univariate margins of all those random variables, x1, x2, blah blah blah. Okay, and here we denote them f1 hat. So f1 hat is your estimate of what the univariate CDF of x1 is, and so on. Fk hat is the estimate of the CDF of xk. Now I say assume you have those estimates and you know how to do this. You know how to fit univariate data to a specific distribution. But then if you have those univariate CDFs, you can use the well-known relation that the CDF of any x, if you plug it inside its only argument x itself, you have a uniform. That's a well-known probability result, of course, for continuous x. Okay, so just make sure you agree with this. Okay, if fx is a CDF of any variable, let's say an exponential, and inside you plug a random variable that is exponentially distributed, the result, this thing, you can view it as a random variable. It has a uniform 0,1 distribution. But that is exactly the trick we can use to transform our data that here has whatever margins to data that has uniform 0,1 margins. And we do that simply like this. And we obtain what is often called a sample of pseudo-uniforms. And here, pseudo-uniforms, we're going to call them, again, this is bold. So bold hat 1, bold U hat 1, bold U hat 2, etc., up to bold U hat N. and those are defined like this. Any one of them, u hat j, is going to be a vector of uj1, uj2 up to ujk, where what is u hat j1? It is this. It is your observation xj1, but that you evaluate at its CDF, because remember, 1 here refers to the first random variable, this one, x1. So if you evaluate, and xj1 is just the jth observation of it, but so xj1 as a certain distribution, you evaluate f hat 1 at xj1. The point is, this thing is approximately a uniform 0, 1. Approximately, yes, because we're using the estimates of the CDFs. If a higher power had told me what the CDF is exactly, meaning if I knew exactly what f1 is and I knew exactly what f2 is, blah, blah, blah. So here I wouldn't have a hat. I wouldn't have estimated the CDF. Then I would have the exact result, of course. I would have that f1 evaluated at xj1 would be exactly a uniform. But in reality, we need estimates of we need to have estimates of the margins. What we have is an approximate result. This is approximately a uniform 0, 1. And same thing, this one is also an approximate 0, 0, 1, uniform 0, 1 random variable, and this one as well. I mean, all of them. And now, basically, I have what I want, because I have transformed my sample that didn't have uniform margins to a sample that has, at least approximately, uniform 0, 1 margins. And this is great because now the joint CDF of this new sample, the joint CDF of any of those observations you had J, is the copula C theta. Approximately, and the only reason I say approximately is because the margins uj are only pseudo uniforms. They are not exactly uniform 0, 1. And I mean, how close they are to uniform 0, 1 would depend on how good your estimates of the margins are. Yeah. Now, conceptually, maybe something that I should have said before, but here what we're doing is we're assuming that this x, this vector, admits a certain copula that I'm calling big C theta. Now, I hope it's clear that the transform sample, okay, this sample, the u's, they have the same copula as x. Well, yes, because this is an increasing transformation. Okay, any CDF or estimate of a CDF is an increasing function. So the copula of x is the same copula as u, but now u, the margins are now uniform 0, 1. So I don't need to care about the margins. That's the whole point of this transformation, is that here there are no more parameters that have to do with the margins. You can say that the distribution of those u's, again, bold u, it's a vector, is the copula C theta, which copula will exactly the same copula as the x, again, because we've just transformed the data with an increasing transformation. Well, increasing transformations, plural, because there's f1, f2, fk, blah, blah, blah. Okay, and so now we can do the fitting by maximum likelihood. We're ready to do that, because now, again, assume that big C theta is the copula we want to fit. And by fit, I mean, we assume the data as this copula, and we want to estimate the parameters. Okay, that's what we mean by fitting. Now, this copula has a certain copula density C theta that I can use to write the likelihood function and then maximize it, as we do in the univariate case. Okay, and again, I call theta bold the vector of parameters. There could be only one, but there could be several. And so yes, the maximum likelihood estimators of those parameter theta is obtained by maximizing the following thing. But let's explain. The whole trick is that C theta doesn't have any parameters that have to do with margins, because C theta, little C theta here, is a density, a multivariate density of uniform margins. So the only parameters that are in C theta are the parameters of the copula, big C, and are the parameters that have to do with the dependence. So if I have observations with the density C theta, that's great because I can just maximize the likelihood of those observations, and I'm going to obtain the parameters of the copula. There are no, here in this expression, there are no parameters that have to do with the margins. So this explains all the trouble we've gone through to define a sample of pseudo-uniforms that I now use to write the likelihood, well, the likelihood of the likelihood I want to maximize, because it's the likelihood that contains only parameters of the copula I'm fitting to my data. Okay, so I don't know if that makes a little bit of sense. I understand it's a little bit theoretical. Again, we're going to try to illustrate all this fitting in R in the next video. And here, I mean, nothing is especially complicated here. I'm just doing the usual thing that I take the log of the likelihood, because this is then just the sum of the log of the individual densities. Now, careful here. This is a multivariate density, of course. Okay, the U is still a vector, and I mean, maybe I should write it. What's the likelihood of my data? Well, it's C. This is little c, okay? It's little c theta. Remember, this is a density of the copula with uniform margins. But now, because I have made the work to obtain uniform, I can plug just here the first one. I can plug, this is my first data point. It's a vector. So here, because I don't know how to do a bold, maybe I'll just write arrow. That is a usual convention to have a vector. Okay, so the vector, the first uj as defined here, well, u1. Okay, but now the likelihood is just the product of the individual densities if I looked at all the observations. But it's just that here my observations are multivariate, blah blah blah, times C of un. Okay, and again, un is the, well, I should write u hat here, u hat, but it gets a bit cumbersome. Okay, and then if you take the log of the likelihood, well, you're just gonna get this, the sum of the logs of the density evaluated at the observations. Okay, here there's just a note that of course here we didn't say much. We just said we assume that we have estimates of the CDFs, but again, this is something you know how to do. And there's several approaches, of course. To find those estimates of the univariate CDFs, you can just use maximum likelihood. In practice, I think what people do when doing copula fitting is mostly they're going to estimate those empirically. They're not going to even bother, if they're interested in just fitting the copula, at least they're not going to bother to fit those to specific distributions. They're just going to use the empirical CDF. You know, by empirical CDF, I think you know what I mean. You know, f1 hat 10 would be, if it's evaluated at any argument, would be all the values of the first argument, the first variable. Well, I should write the indicator function. Okay, we're just counting how many times the x1 was smaller than little x. Okay, little x being the argument of the, and then we divide by n. Okay, so it's empirically estimating the probability that x1 is smaller than any argument little x here. Okay, here, as usual, my handwriting is not so good, so let me just rewrite. Okay, we're counting how many times x1 was smaller than little x. Okay, where little x is the argument over here. Okay, and you know, xj is here, whether it's x11, x21, x31, etc. Okay, and that's the second option. And we even saw a third option. You could use potentially extreme value theory if you have data that's very heavy tailed. Maybe you want to fit the tails, okay, the exceedances above a high threshold to the generalized Pareto distribution. That could be another options to estimate the margins here. Okay, and now, so here the approach we just covered, okay, from here to here, it is fitting the margins and the copula separately. Well, yes, because in some step we estimate the margins here, and then we do the trick to obtain pseudo-uniforms, and we use that to fit the copula here. In principle, you could fit everything together in one big maximization step. Well, yes, because you can write the joint PDF of the x, the vector x, x1, x2 up to xk. You can write it explicitly if you have a model for every margin and if you have a model for the copula. Well, yes, you can write the density like that. And where does this equation come from? It comes simply from Sklar's theorem. Here, careful, it is indeed the little c, the copula density, evaluated at every margin, f1 of x1, f2 of x2, blah, blah, blah. Here, of course, this is a multivariate CDF, so its argument here is a bold x. Bold x means x1, x2, x3, up to xk. But then careful, you multiply then by this thing, the univariate CDFs, not CDF, densities, the univariate densities evaluated at every argument. I was saying, where does this come from? From Sklar's theorem. Just look at Sklar's theorem and then differentiate it k times with respect to every x, and by the chain rule, you will obtain this formula. Well, yes, let me just show you or remind you. Sklar's theorem is here. Okay, that tells us we cannot always express a joint CDF by the copula, the big C, evaluated at all the individual CDFs. Differentiate this with respect to x1, x2, xk, x3 up to xk. What's going to happen? Well, once you've differentiated the big C k times with respect to all the argument little x's, you will the big C will become a little c. But every time you differentiate it by the chain rule, you will differentiate those arguments that are fx with respect to the x. So one time when you differentiate with respect to x1, there's going to be a term here that's going to get that will be generated, which will be the derivative of this with respect to x1 is going to be fx1. And then when you derivate with respect to x2, you're going to have another term that's going to be fx2, etc. Okay, so in the end, you will obtain what is over here, this formula. Now, and the point of this is simply that you can then write the likelihood, the full likelihood of your model. And by model, I mean a model where you have chosen a certain margin for every random variable, and you have also chosen a copula. The likelihood of your data is then simply, as usual, the product of those multivariate densities. And so in principle, you can then view this as one big multivariate function that has lots of parameters in it. Well, yes, because it has all the parameters that has to do with x1, the parameters that have to do with x2, etc., and it has the parameters of the copula. So you can maximize this in principle, but the problem or the potential problem is that maybe you have a lot of parameters there, and then usually you're gonna, optimize this in R or with a software, and maybe you're gonna have trouble to make your algorithm converge if you have so many parameters to fit at the same time. But in principle, you can do it. So here there's a comment. Using pseudo-uniforms, copula data, okay, the two steps approach is easier. Just be careful that it could give biased results due to the noise from fitting the margins first. Here, basically, you need to make sure those things that you pick to estimate the margins are sensible. Because if you've picked the wrong margins and then you do the copula fitting, well, those pseudo uniforms won't be close to uniforms at all. And then when you do the fitting, when you do the maximizing here, those U's, they are not observations from the little c, and so it doesn't really make sense. You might not get good results. Okay, so if you've done errors in the first step, they will accrue in the second step. And again, this will be illustrated. We're going to actually try those methods in R, and we'll see that yes, if we've picked a terrible choice for the margins, we won't get a good estimate for the copula parameter. Okay, and then one last slide. I'm not going to say too much about this. I'm just going to explain it conceptually. Obviously, you can't, in reality, just pick a copula, fit the parameters, and then your work is over. Maybe you haven't done a good choice of copula. So there would be one other step, which is assessing the goodness of fit of the copula you've picked. And here we've put the reference that is much cited paper on this topic that reviews lots of different methods. But anyway, by goodness of fit, what we mean is simply this: we want to explicitly test the null hypothesis that the copula of X is the one we've picked. Because again, what we're doing here is we have our multivariate data, we've picked some copula C theta, we've estimated the parameter, but maybe this copula is not doing a good job at representing the dependence. So then we want to test the hypothesis, okay, is my choice correct, or is it reasonable that this specific copula C theta represents the dependence of my multivariate X. And there are many test statistics in the literature to do this. We present just one here that has a relatively simple form, and it's a so-called Kramer von Mises, don't know if I pronounced this right, probably not, approach. And so under this approach, this is the test statistic. Let's just understand it conceptually, but again, unfortunately not presenting all the details here. It is the sum of square differences, the difference between those two things, C tilde and C of theta hat. What are those things? Well, C tilde is what we call the empirical copula of the data. Now, I'm not presenting what this is. It's frankly, it's not especially complicated, but here, I suppose, in the interest of not overloading, I'm not going to present what this is, but just view it as conceptually analog to the univariate empirical CDF. So when you collect data, you can easily compute an empirical CDF that gives you the probability of data point is small or equal to whatever argument. There is a way to generalize this and define a empirical copula, which would be then a multivariate CDF, well, with uniform margins. But again, sorry, here I'm not presenting exactly what it is in terms of a specific formula. But just conceptually view this as, yeah, the copula of your data, but without any parametric choice. It is purely based on the data without having to do any assumption about what the copula is. On the other hand, you have the model that you've picked. So this is a specific copula. So let's say that you have fitted your data to the Gumbel copula. Well, C theta here would be the Gumbel copula, a specific parametric choice. And you see, and theta hat represent the fitted parameters. As we've just explained, you can find the parameters of your copula. So this is what we mean by the fitted theta hat. And you see now, this represents purely your data. There's no parametric choice. Okay, the green one. The blue one represents your model, the parametric choice you've picked. Okay, the specific copula you've picked, like Gumbel. Now, you evaluate this at all your data points. Well, okay, here the U hats are the pseudo-uniforms, but they are still your data points. And you take the difference. I'm just here, I just want you to understand conceptually what this is doing. If the empirical is close to the fitted, it means the fitted does a good job because you've picked a choice, a parametric copula that is close to the empirical copula, and that's good. So if this difference is small, it's good. The test statistic will be small, and we will not reject H0. On the other hand, if for most points, or at least some points, there's a big difference between the empirical copula, the copula of the really of the data, and the fitted parameter, the fitted copula, the parametric copula you've chosen. If this difference is big, then your fitted model doesn't do a good difference, doesn't do a good job, because there's a difference between the data and the fitted model. And then this test statistic will be big, and then you will reject. So that's the logic of it. And frankly, that's all you need to understand. And this specific test is implemented in the R package that I'm going to present again in the next video. So again, let's just read the conclusion. Large values of the above test statistics make us reject that a given copula generated the data. And also, I mean, we're not going to present how to obtain critical values. It's slightly complicated. We will let R do the job for us. And of course, the good people who have implemented those tests in R. Okay, I know this was kind of heavy. I hope it made a little bit of sense. Maybe you'll have to review those slides, and perhaps watching the R demonstration will help cement those theoretical concepts. But if you have any questions, of course, send them my way, and I will see you soon, hopefully. Okay, bye for now.